So the next one of these syn eliminations, which should be C in the list, is the Cope elimination, which uses amine oxides. The Chagayev, remember, used xanthate esters. And amine oxides aren't so hard to make. You just start with a tertiary amine and you oxidize it with something like hydrogen peroxide. Now, if this were a phosphine oxide, you could write it with a double bond here. But remember, nitrogen is just in the second row, so it can't expand its octet. So that has to be a plus-minus bond there. But nitrogen tends to do that quite a lot in its bonding. So these are stable compounds that you can isolate. And then at 100 to 200 degrees, this will eliminate and give us this is dimethyl hydroxylamine or dimethyl hydroxylamine if you prefer, and our alkene. And this is another one of these pericyclic reactions, this time with just a 5-membered ring transition state, but still an aromatic one because it's remember, we can have 5-membered ring aromatic compounds, and this is kind of analogous to that. So 5-membered ring transition state gives us the alkene. But there's one that can go even lower than this, a little bit lower anyway, and that's to heat a sulfoxide, or if you want one that goes at room temperature, use a selenoxide, and I'll show that next. So we can also use a sulfoxide, which is quite similar in many ways to the amine oxide that we saw before. And a sulfoxide can likewise be prepared from a thioether, or sulfide as it used to be called. So the same kinds of oxidizing agents that we used with amine oxides. Now sulfur can expand its octet, so we can write this with a double bond, but just so you can see the similarity with the amine oxide, I'm going to leave it in this form, which is actually a major form, because any double bond is actually a D to P overlap rather than a usual pi bond that we're used to. So sulfoxides are very stable compounds. You may remember from Chem 341, DMSO, cold DMSO for SN2 reactions. And DMSO is just dimethyl sulfoxide. So these things are very stable at room temperature. But if you heat them up to maybe 150 degrees, I have 80 degrees. I've seen it as high as 150. And we get our alkene again. And we get this sulfenic acid byproduct. This will often decompose, or it may be removed. Sometimes people will add phosphates or things to remove this and prevent it reacting with your main product. And again, this involves one of these pericyclic reactions. Yeah, that's pretty good for temperature, and like I said, sulfoxides are pretty easy to make. Selenium is directly below sulfur in the periodic table. So we just write an E after these S's all the way through, and it goes through the same mechanism. And selenoxides are in fact unstable at room temperature. So that sounds great, and so these sound perfect, except there's one problem with selenium, and that is selenium compounds are very toxic. So really, this would not be something you would use with selenium on a large scale, but if you're just trying to make a few milligrams in the lab, then it's okay. Now, people do use this kind of chemistry to do some nice little tricks. And so one way, for instance, if you want, and we are really covering how to make double bonds here, so this is a nice way. What happens if you have say a ketone and you want to take it from a saturated ketone to an unsaturated ketone? So I'm talking about a sequence like this. Well, you can use this chemistry to do that. So first of all, we start with, I'm going to show the hydrogen that's going to be lost here, and I'll show the bonds on there. You have to have a hydrogen on here. So LDA, that gives us the enolate, and enolates react with disulfides or diselenides, and these actually have a selenium-selenium bond in there. It's quite weak, so these are a little bit like I2 or something like that in many ways, and so you can then prepare our seleno ether or selenide like this. That's a bond there. I'm not sure how clear that is in the video. And we can then take that selenoxide and treat it with the selenide, treat it with H2O2, and that will give us and remember, this will decompose spontaneously at 25C. So we'll get so sorry I had 5 bonds of carbon there, but so we get an enolate form. We do phenylselenation at the alpha position to the ketone. There's only one group attached there. Then oxidize that to the selenoxide. It decomposes around room temperature and gives us our unsaturated ketone. So that's used for that sequence there. And although it looks long, you can see it's pretty quick to do. So.